Hello everyone, my name is Peter and today I'm going to present to you our work titled Utilizing Parallelism in Smart Contracts on Decentralized Blockchains by Taming Application Inherent Conflicts. This work is a joint work by the Shanghai Treegraph Blockchain Research Institute, the Shanghai ICSE' Institute, Duke University, Tsinghua University, and the University of Toronto. So the problem that we are looking at is that Ethereum and similar blockchains, they execute transactions serially. Now, in many systems, the consensus might be the bottleneck, but some recent innovation in Conflux and some other systems managed to eliminate the consensus as the bottleneck. So the new performance bottlenecks in terms of the hardware resources could be network, storage, or transaction execution. We argue that the latter one, transaction execution, is the hardest one to tackle, so that's what we are looking at in this work. So our goal is to speed up execution through parallelism without fundamentally changing the programming model or the protocol of the blockchain. And the goal that we are hoping to achieve is potentially better scalability, higher resource utilization, and quicker node synchronization times. Our three main contributions are summarized in these three questions. First, what is the amount of parallel speedup that we can expect on Ethereum? Second, how can we eliminate some bottlenecks that limit this parallel speedup? And third, how can we make parallel execution on blockchains deterministic? But first, let me briefly introduce the execution model of Ethereum and similar blockchains. So on Ethereum, transactions are divided into batches called blocks, and execution happens block by block. So when a block is executed, the Ethereum virtual machine, EVM, receives a list of transactions as its input, and it also receives the current state of the system as its other input. And through executing the transactions on this state, it produces an updated state. So it's basically just a state machine, and the unit of execution is the block. Now, when we look at the state, it's actually a Merkle tree. So it's a tree-structured global storage that consists of accounts and smart contracts. So some nodes are simple accounts that record things like balances, and others are smart contract accounts, which in addition to the same fields as accounts have, also have their own local storage. And you can conceptually think of this storage as a subtree in the contract account, under the contract account. When we execute smart contracts, the execution is triggered by a smart contract transaction, and it can actually execute arbitrary code. And it's only limited by the cost associated with every instruction that is called gas. Each transaction could theoretically access any part of the global state. For instance, in this example, we trigger the foo function on an account, and it will trigger a write to the smart contract's own storage. However, it could also trigger a smart contract call to another contract, so it could also modify the other storage. So what we are really talking about here is a global shared state that transactions can read and write. So it brings us to the first question: how much parallel speedup can we expect on Ethereum? To find out, we looked at historical transaction traces. We collected storage access traces for transactions, and this gives us information about the dependencies between transactions. So normally, transactions are executed serially, and this is our baseline, the serial execution time. But based on this information, perfect information about the dependencies between transactions, we can derive an optimal parallel schedule. In this example, on the figure, we derived an optimal schedule for 2 threads for these 5 transactions. And what we do is compare the execution time of this schedule to that of serial execution. We did this for hundreds of thousands of blocks of historical Ethereum transactions. And what we found out is that the overall parallel speedup is far underwhelming. So even if we used 4, 8, 16, 32 threads in our simulation, the overall speedup that we could achieve was only 4 times compared to serial execution. If you look at the figure, you could see that some blocks have good speedup, 16 times or even more parallel speedup. However, a big portion of the blocks is actually much slower, only 2 to 6 times speed up, because they are bottlenecked on a series or chain of transactions. Now, we argue that this evaluation is based on perfect information, so any real-world scheduler can only do worse than this 4 times speed up. So this is definitely an issue. As a next step, we try to understand what was the root cause behind these bottleneck transaction chains, as we call them. And we identified 3 main categories of applications. The biggest category is ERC20 token transactions and token distributions. The second biggest one is decentralized finance applications. And the third one is games and collectibles like NFTs. We also looked at the root cause in terms of the programming constructs associated with these storage conflicts. And what we noticed is that the big majority of them are associated with integers, basically counters, counter increments, or adding a number to counter, these kind of operations. And a smaller part is associated with arrays in Solidity. So here's an example of an ERC20 transfer. The 2 main operations are, first, we decrease the balance of the sender, and second, we increase the balance of the receiver. So you can see that if we send many transactions from the same sender, they will decrease the same balance. So they will all have a dependency on each other. They will all conflict. And this is a very common phenomenon that we observe. Now that we understand that currently Ethereum is bottlenecked in terms of parallel executions of parallel speedup, is bottlenecked on these conflicts, the question becomes, how can we eliminate these conflict patterns? And we propose 3 techniques for this. The main idea is that if we have a long chain of transactions that need to be executed serially and thus dominate the overall execution time, what we want to do is break this chain up into multiple disjoint dependency chains. In this example, we broke it up into an orange and a green chain. And these 2 dependency chains or transaction chains can be executed in parallel. And through this, we could reduce the overall execution time and increase the speed up. So the first technique that we propose for this is called conflict-aware token distribution. As I mentioned, token distributions in the majority of cases happen in a way that we have a single sender account and this sends many transactions to different accounts. Now, all these transactions will conflict because the same sender balance has to be updated for each transaction. So these transactions need to be executed in a serial fashion. Our proposal here is that instead of using a single sender account, we could use 2 or more. So in this example, instead of using the single account S, we use 2 accounts, S1 and S2. And this way, the distributions from these 2 accounts can be executed in parallel with each other, and we could reduce the execution time. The second technique we propose is based on earlier work called sloppy counters. And we call it partition counter in our work. The idea is that a single counter object under the hood would consist of an array of integers, so multiple storage entries. When you write to this counter, so let's say you add a value, you choose one of the entries in the underlying array based on some criteria. In this example, we choose based on the transaction sender address. As a result, 2 transactions that update the same counter, if they come from 2 different senders, they have a lower probability of conflicting with each other because with a higher probability, they will update different storage locations. If you read the counter, of course, you need to sum up all the locations. So this will conflict with any other operations. So this approach is more suitable for write-heavy workloads and write-heavy counters, which in our estimation or observation is quite common in Ethereum. And finally, we also propose a new instruction called commutative operations. Let's look at this example. We have transactions 1 and 2, and both of them are incrementing a counter. The way this is translated or compiled into EVM bytecode is that it's compiled to a load, an add, and a store operation. And you can see that transaction 1's store operation will conflict with transaction 2's load operation. So transaction 2 will need to be aborted and re-executed. However, we argue that from the application's perspective, a simple counter increment is actually like semantically commutative. So the application doesn't care. We could reorder transaction 1 and 2 into any order, and the resulting state would be the same. And this is true for many applications. But because these are compiled into load and store operations, they will always conflict. To handle this issue, we introduce a new operation called commutative add, CADD. The idea is that two commutative add operations executed in parallel will not conflict as they are executed lazily. So transaction 1 and 2 could finish execution here. And during commit time, the scheduler can collect all the updates to the counter and execute them one by one in a serial fashion. This way, even though both transactions increment the same counter, they don't need to abort, and we can execute the transactions in parallel. So to summarize this section, we propose 3 techniques for alleviating these bottlenecks of parallel execution. On the user level, users can use conflict-aware token distribution. On the developer level, developers can choose to use partition counters. And if we are willing to change the virtual machine, we could add commutative operations to avoid conflicts. And this brings us to the third contribution of our paper. How can we make parallel execution deterministic? So in blockchains and generally in replicated state machines, determinism is very important so that different nodes executing the same data set, the same transaction set, will reach the same result, and thus they can reach consensus. Classic optimistic concurrency control, OCC, has no determinism guarantees, so it's not really suitable for this requirement. But there has been a lot of work done in deterministic database systems with deterministic OCC, which guarantees the same serialization order on different nodes. So this results in the same state. However, the exact execution might still differ. Let me show an example to explain this. Let's say we have 3 transactions and we want to execute them on node A first. So first we schedule transactions 1 and 2. They can be executed in parallel and they do not conflict, so they can be committed normally. Transaction 3, as you can see on this example, actually depends on transaction 1. It reads value written by transaction 1. However, they are executed in this order, so it's fine, and then we can commit transaction 3. Let's assume, however, that node B chooses a different schedule. It actually starts with transaction 2 and 3 being executed first. At this point, we cannot commit the transactions yet because we need to keep the same serialization order. So we need to wait for transaction 1 first. Transaction 1 is executed. And at this point, we can commit transactions 1 and 2 because they are independent. However, at this point, we notice, or the scheduler can detect the conflict between 1 and 3, and it will decide to abort 3 and re-execute it before it can commit. Now the resulting state would be the same on different nodes. However, we argue that in blockchain systems, we need to associate a price or a cost with the aborts, because this is the only way that we can prevent spamming the system or denial of service attacks on this parallel execution mechanism. And if we associate a price with aborts and different nodes make different abort decisions, then the state will diverge and nodes will be unable to reach consensus. To solve this issue, we introduce a new OCC variant called OCC with deterministic aborts, OCCDA. Let us look at the ith execution of transaction N. So a transaction can be executed 1 or more times depending on the abort decisions. In OCCDA, the ith execution of transaction N must either commit on all nodes or abort on all nodes. This is the property that we're looking for. To achieve this property, we want to specify the state that the ith execution of transaction N can see. Moreover, we want to specify it in a deterministic and uniform fashion on all nodes, and we will call it storage version. For instance, the first execution of transaction 3 might see state 0, that is the state before the block's execution. And the second execution of transaction 3 might see state 2, that is the state after transaction 2's execution. There are different heuristics as to how we define these storage versions, but the main requirement is that they need to be defined the same way on all the nodes in the network. Let's see how OCCDA helps us solve the issue that we just showed in the previous example. Node A, as before, it will start with scheduling transactions 1 and 2 in parallel, and they can be committed as usual. When we finish execution of transaction 3, the scheduler actually notices that the first execution of transaction 3 is not allowed to see the results of transaction 1. So even though it technically could see the updates, it will still be aborted under OCCDA. After the abort, we can reschedule transaction 3, and the second time it can see the updates and commit. So you can see that using OCCDA, the first execution of transaction 3 aborted on both nodes, and the second transaction of transaction 3 committed on both nodes. So we actually managed to ensure this property that we laid out in the previous slides. Now that we've discussed OCCDA, and we also discussed the 3 conflict elimination techniques that we propose, let's look at some evaluations. In our evaluations, first we looked at the effect of partition counters on the speed-up bound of transactions. So we used the same approach as with the earlier experiment. We look at perfect information of transaction dependencies, and we look at the best possible schedule on a parallel scheduler. Our baseline here without any partition counters is 9 times speedup compared to 0 execution. When we applied the counter of size 2 to all the conflicts, this actually doubled. So the maximum available speedup that we could achieve rose to 18 times compared to serial execution. We'd also like to mention that on this dataset, if we remove all the dependencies, then the highest possible speedup achievable is 23.6 times. So what we can observe here is that as we use counters for our conflicts, counters of size bigger and bigger, we're actually converging to the optimum or the theoretical maximum possible speedup in this dataset. Second, we looked at the performance impact of OCCDA. So as you saw in the previous example, in some cases, OCCDA will abort transactions even though they could theoretically be committed. It will abort these transactions in order to ensure that all the nodes in the network reach the same abort decision on transactions. So we expect it to have some performance impact or some performance trade-off through this. What we did here is we ran simulations on historical transactions using a traditional deterministic databases OCC approach and compared it to an OCCDA algorithm approach. Our finding is that, in fact, there is a performance impact of OCCDA, but this impact seems to be well within the acceptable bounds. And these results suggest that OCCDA might be suitable for using real-world blockchain systems. So to summarize, we observed that parallel execution on Ethereum is often bottlenecked by a chain of conflicting transactions. And these conflicts are inherent in the programming model and the applications on Ethereum. To solve this issue, we proposed 3 different techniques, and these techniques can help eliminate some or much of these bottlenecks in the Ethereum programming model. We also proposed a new OCC variant called OCCDA, which will allow parallel schedulers running on different nodes to reach consensus, even if we assign incentives to commit abort decisions on these nodes. We believe that our work has laid the groundwork for future protocol innovations, and it can ultimately lead to and enable parallel transaction execution on Ethereum and similar blockchains. Thank you very much for taking the time to listen to our presentation.